Okay, I'm a little bit out of breath here from carrying our next project down the steps and getting it up to the bench. Now this is going to be a really interesting thing, and I'm going to kind of pan up onto it here. And if you look, it is a bell ringer amplifier. And what this is out of my church. Back in the 1950s, my church purchased this refrigerator-sized cabinet, and basically what it is 4 kind of giant cartridge tape machines, tape decks, all stacked on top of one another. And on the tapes is bell music, like church bells. And the whole purpose of this back in the day was you mounted the big speaker to this up in your bell tower, and you wired it into this rack, and in this rack there were 2 amplifiers and 4 tape decks and a mechanical clock that would set the bells to chime or to play at certain times during the day. So lo and behold, the other day I guess it quit working, and they asked if I would take a look at it. Now you might say, well, how interesting is that, working on a little amp from a bell tower? Until we look at the other part of this. Let me back up, and this is why I'm holding the camera. And if you look, you guessed it, these are Macintosh power amplifiers from the 1950s. And if we pan up over the top here, we can see they're actually one of the earliest solid-state Macintosh amplifiers. See the big potted transformers that we're used to seeing, and I'm no doubt these are probably germanium output transistors. You see the driver board, all very heavy duty. I would imagine similar amps to this were what was used when they, from what I understand, the Woodstock concert, when Woodstock played. I heard that was all played through Macintosh PA amplifiers, and I'm sure they were similar to this one. So this is going to be a pretty exciting project. The bell tower actually has 2 of these amplifiers in it. And I have both of them here, and they're coupled to a little preamp. And you can see there's not much to it. It has a phono, a tape, and a microphone input, and a single channel output, and a power input, which the other end of the cord is still in the machine, but it plugs into a preamp power output and the signal input right here, along with a level control. So we're going to go through these whole amps and this preamp, rebuild them, hopefully back like new, with modern components wherever we can, but try to keep the original sound integrity that these had. And normally I wouldn't get so excited about just an amplifier or PA amp or something, but I think these are going to be interesting. I've not downloaded any of the schematics yet, but I am going to search. I don't even know exactly what model these are, because they just came in today. I just put them on the bench. So like I said, for the next couple videos, come along with me as we work on some vintage Macintosh solid-state gear. So let me find out some more info, and I'll be back. Okay, we're back. So here's what I found so far. What this seems to be, the model P237, was a special design amplifier by Macintosh for the Verdin company for their bell system. It's basically a modified Macintosh MC100. Now before you get too excited, the only MC100 book I can find online was only partial. It was 7 pages, and it showed schematic for the input board, a little layout of the transformers and so forth, and the power supply, and a parts list. However, the listing for the schematic for the actual power amplifier is missing. Now, it is also supposed to be very similar to an MC2100, which is two MC100s in one chassis, pretty much. Now, I'm not sure this one, if it's exactly going to be the same or not, but there may be enough similarity in these schematics to at least get us on the right track as to what we're looking at. So, one channel here, okay, half of this would be pretty much what we're looking at. So, as you can see, quad outputs, and that's what we have. Two drivers. So it looks very similar, and the unique thing about this whole thing is the output transformer that they use. Now, another difference, the MC100 and the MC2100, being a commercial, local, home use amp, has a power cord and everything. If you look at these Verdin amplifiers, you basically put your 110 volts in here. Okay, so you have ground and 117 AC, and then right next to them you have your speaker outputs, which by the lowest impedance speaker this thing can handle is a 16 ohm. And Verdin has also, or somebody at some point in time, has attached this 50 ohm power resistor and had it wired into this. So I think what that indicates is these amps don't do very well with any load below 16 ohms. And these are probably germanium transistors, which really don't like low impedances like that. Don't like to go below their intended impedance. So needless to say, this is going to be a little challenge to figure it out. And I think the first thing I'm going to do is get this apart, take kind of an inventory of the components, and look at them. I can already see some capacitors that have blown open in here. Who knows how long they've been like that, but definitely going to have our work cut out for us on this one. And again, one power transformer and one output transformer. And yes, it's a it's a solid state amp with an output transformer. This is what they did to match the impedance to the amp, so that no matter what impedance, the amp can deliver its full power output. If you recall, on most solid state amps, they give you a rating for the output of the amp at 4 ohms and the output of the amp at 8 ohms, and they're always kind of like double one another. So whatever it puts out at 8 ohms, it puts out up almost double. So an amp that's putting out 50 watts into 8 ohms, they'll rate it at maybe 80 or 90 watts at 4 ohms. The unique thing about these is, because of this transformer, it matches the impedance, so the full power is always delivered to every impedance. Very interesting. So we're going to look at that, and as much as I would really like to keep this perfect original look, we may have to put some modern capacitors and things in here, depending on what we find that fails. Again, these amps are going to be put back into use, and it was made very clear to me that more than keeping it original, they want to keep it functional because they want to continue to use the device. So that's what we're going to do. We're going to respect their wishes, and I'll try to do as little as possible to change the amp. And certainly won't do anything to change its performance in any way. I want it to sound just like it used to sound. Okay, so let's get some covers off and get it apart and start looking on. Okay. Few surprises here. First of all, when we look underneath here, there's not a whole lot to see. You've got two gigantic capacitors, and as massive and huge as they are, they're really only rated at about 9,300 microfarads at 50 volts, so they're less than 10,000 microfarads, which for a 100 watt amp, 10,000 microfarads is, in today's age, would be pretty slim, but back then would have been a lot of capacitance. We can see a couple things here. We have a thermistor that looks, if you look down here, we have a thermistor that looks kind of cooked. You can see right there what I'm talking about. It's taken a hit. So that could be part of our problem. The other pleasant surprise I found was on the from the top, you can see 2 transistors on each heatsink, which would lead you to think there's a quad setup, 4 transistors. But down, you get here down to the bottom, there's a third one. So there's actually 6 transistors on the outputs of this. We can also tell there's been quite a bit of work done to these over the years. Somebody's replaced diodes randomly. They don't match. They're different types. Those are all going to need to be replaced with proper replacements. The transistors have been replaced over the years, you can see, and as you can see, these were just barely, the solder was just tacked on, not properly at all. Bubblegum solder. I have a short almost between these two, so if we tip this up, very heavy, you can see where that's almost touching there. Let me zoom you in. So, you have people that work on these things, and they don't have the proper tools or the proper training to work on these high-end type of devices, and this is the kind of stuff you see. But I'm not going to rip on anybody. I mean, people did what they could with what they had at the time. So you can see our power transformer comes in here, our output transformer comes in here. There's all our lacing and wiring. The wires look beautiful. I mean, even though they're wax cloth covered wires, they're still pliable, they're not crusty, really good shape. So really, under here, we're going to need to do some diodes. We're going to need to check all our transistors and remove them, re-grease them, put them back in. They don't appear to be up on heatsink pads, which is kind of strange, but and everything's kind of tied together here, but I would have to look at the schematics to understand why it works like that. But needless to say, we'll check that all out. Or maybe they need to be isolated, somebody replaced them, and this thing hasn't worked in forever. I don't know. I know when I did hear it play, it always was very distorted and not very loud, so this could have something to do with it. So check all the resistors, the few that there are, make sure they're in tolerance. And I guess after I do a little bit of more research on these, I'll be back. I do have a good parts list for an MC100, and I'm thinking that if I look at this, it should give us a little indication what these need to be. So we can see signal diodes, silicon rectifiers. We have the transistors here. So maybe we can take these part numbers from Macintosh and convert them over to actual part numbers. I don't know yet, but we'll try to do the best we can with what we have and solve this puzzle one piece at a time. All right, and then you can see there's a 4-section electrolytic. There it is, 1, 2, 3, 4, and it's 80, 80, 150, and 50. And these are all small capacitors today, and what I may do is I'll keep these top ones up here the way they are, and I may mount some smaller modern capacitors under here in a way that it won't really interfere with. I'm not going to drill holes or anything. I'll use existing screws to put up some circuit board or something that I make up so they can all be reversed if we ever want to make it back to original. The other thing is these output capacitors may be good. I highly doubt it, but with their age and all, it looks like this whole system could not have come out in the 50s as I was told. This amp, the P series, is made only for Verdin. They only made it for 2 or 3 years. Rumor has it there were less than 400 of these made, closer to 350 or so of these ever made, so they're super rare. And their date of production would have been 1969 to 1971, somewhere around there. So we're talking 2 or 3 years max that these were made. And that would make more sense with these transistors, because the transistor really didn't even come out until 57 or so. And so you figure you wouldn't see big transistors like this or power transistors until late in the 60s. So that would make sense for this. 1950s just didn't make sense to me. So more than likely that is like a 1969 or 1970 is what I'm dating this at. Now I'm sure if we had a way to look up serial numbers and things, this is 1162, we may have an idea. And that's the other thing, I'm not sure what that serial number means. If that means, you know, they made 1,162 of these, or if the 1162 is a code for a date, 11th month of 62, but that would still have to have another delineation number if there were multiples of these made in that month. So something in here we'll have to figure out. We don't know the way Verdin actually serialized these from Macintosh. So let's get things apart and start testing, and as I test the components, we'll go along together on this and look at it. We'll check ESRs of capacitors and things like that, and we'll move on from there. Okay, right off the bat, you can see I'm on this first 9300 microfarad capacitor. And what this is saying is it's only reading about 3300 microfarad. And I'm looking at the ESR, it's about 3.2 ohms, so it's rather high. I don't know what it should be for this capacitor, but I would kind of think that's a little bit high. But it is reading very low. Now I'm reading it at 120 cycles, which would be just the same as if a full wave rectified signal would be applied across it. So if you put a full wave rectified 60 cycle waveform across here, this is basically what type of capacity you would see here, which is about 3,300, which is a third of what it should say. Okay, and again, I have nothing connected to it, so this is just the open terminals. I took everything off. So we will have to, I'm going to disconnect this other one, and we're going to do the same test, and we're going to see how the other one compares. But this capacitor is definitely bad. So let's go to the next one. Okay, so we look at this next one, and our ESR is about 3.9 ohms, a little bit higher. And you can see this one's only reading about 1,800 microfarads. Okay, so again, out of 9,300 microfarads, we're only reading 1,800. And this is to be expected. You have a 45-plus-year-old amplifier with original old-style electrolytics, which were notoriously not very long, longevity, long life. We can expect this to happen. It's been sitting in the back of a church for many years, running for many years. This is to be expected. So we have two pretty much bad capacitors. So let's go down the line. I'm sure as we measure all these, they're all going to read bad. So needless to say, capacitors are going to need replaced. And let's go up top side and see what we get up there. These definitely, you can see by the bubblegum solder job that's been done, that focus in there, you can see these have been replaced. And we don't know, again, none of these can be correct. I mean, these two look original, these look replaced, and none of them are the same type, and they're not really even soldered in there properly. So we're really going to have to clean all this up and make it right. So a little bit at a time, though. So let's go top side. Well, not much better top side. Let's pull this little board out. As you can see, we have a pretty badly damaged capacitor there. These transistors are actually look to be socketed and soldered. They don't all look to be original. And see, these are Jans, meaning these are military, and you can see somebody has marked them with pencil and replaced them. This is an old repair, though, definitely. So all of these transistors will need to be measured and tested and make sure they don't leak. There's no problems with them. And once we do that, we'll have a good idea of what's going on. For the few capacitors that are in this, I'm just going to recap it. I mean, this is terrible. They're all reading way off. So definitely need to look into that. As you can see, one transistor out of all 6 have a insulating pad. I don't know if you can see that or not. Right there, you can see the little insulating pad. And all the rest of them are just directly attached to the heatsink, and I cannot for the life of me, unless those collectors are all tied to ground in the schematic, I just don't see how that can be possible the way it is. So if I go to my MC2100 schematic that I have, and as you can see, here's the board layout of the driver board. There's 2 of these left and right, but if you compare it to the MC2100, which is basically 2 MC100s, which an MC100 is basically a non-commercial version of the P237, same board. I'm sorry, I'm not even on a camera, am I, guys? So here's the board layout, and here's what we have. So you can see, component-wise, same. So we should be on the right track. So that being said, if we flip through here to our schematic, you can see right here the collectors are going to your plus 35 volts, and they're going to your minus 35 volts through some resistors, some current limiting resistors, which, by the way, those current limiting resistors are on the rear here. For all intents and purposes, these transistors are shorted to ground. I mean, that's what it has to be. Here, here's your ground right here, and it is connected to chassis through this capacitor here. If you noticed when I was testing these, all the grounds are tied together and tied to chassis. So absolutely, these transistors are just plain shorted. So I don't see how this ever could have worked. I really don't, guys. I don't see, and that would make sense why this thing is so quiet. Maybe it's out of a church. It is out of a church. Maybe it's a miracle it worked at all. I'm half being sarcastic, but how did this thing work? I just don't know. Very surprising, to say the least. So, and this amp here, there's 2 of these amps. And the way they had it wired at the church was one entire amplifier went to the church bells up in the steeple, or the big speaker in the steeple, which would make sense. You got a 100-watt power amp driving the external speakers to the church. So when they rang the church bells, this amp made that sound. Alright, I'm back. Anyhow, so, wow, where do we even start? So, we definitely are going to need to fix that, and we are going to need to fix the power supply and everything. But anyhow, this 100-watt amplifier drove that. There's a second one of these, equal 100 watts, exactly the same amp, because this unit had 2 of them. And all it was going to was it came out of the speaker terminals and went up to the top of the refrigerator cabinet that this was mounted in. I call it that because that's kind of what it looks like, but it's the actual cabinet for the bell chime system. And there's a monitor speaker. It's not quite a 6x9, maybe a 5x7 oval speaker, little tiny Alnico, 5-watt speaker. And there's a little 70-volt line transformer about that big around. And that whole amplifier went into that. and that's it for monitoring. And it put out maybe 1 watt. And it was distorted, and I'm totally guessing that that amp has been repaired and it has had the transistors replaced as well. So heaven only knows if these transistors are even any good anymore. But we're going to take them out and test them. And we're going to just go one by one, every component. This is such a small and simple build of an amp that meticulously testing everything is not going to be that big of a job. First thing I'm going to do is just showing this to you. I'm getting my hands covered with dust. I'm going to get the dust bunnies out of here, clean it up a little bit, and pull some transistors and test them. And then I'll be back. Well, surprise, surprise once again. If you look at all these transistors and diodes, SI, they're silicon. I would have bet anything that they are germanium. But as it turns out, they're silicon diodes now, and silicon transistors. I tested this first one on my little transistor tester, transistor analyzer, and it's actually very good. It's reading good. I think we may have lucked out by shorting these the way they are. It basically put all the problems onto the power supply and not onto the transistors. Now, what that means is that we may have a bad problem with our power supply. So we're going to have to go through and very gingerly power this power supply up, go through it, and try to find a way to get this thing repaired. But I'm going to check all the rest of the transistors and see how they look and go from there. Alright, so when we just barely touched this burned up thing, it just fell apart. This just came right off. So I have a feeling this amp hasn't worked in a very long time. These transistors in here, you can see that these go to the cases. These little, wait a second here. These go to the cases, okay? So these the ones with the screw terminals go to the case, which is going to be the collector of the transistor. And all the collectors are tied together. All right. So we go from this one to this one, and then from this one, which is the case, all right, we tie over to right here through this one resistor, and then it goes back through this yellow wire. And you can see how that goes. What I'm seeing is that this is all not really matching up the way I would think it should. So you can see this one has been cut and added, and you can see this transistor here, or I mean this resistor here, was not originally in this position. It had been cut and then respliced in, and I don't know, we're going to have to look at the schematic on this to figure it out. But definitely some things in here are not right. Well, I guess found out why this may have partially worked at some point in time. When we look at this, hope I get the meter and everything in the shot here. Let me see. So if we look up here, and you look at my at the transistor heatsink, if I touch my probes together, there's 0 ohms, right? Short. If I touch from this screw to this screw right here, as you can see, I pretty much have a dead short. Okay, it's moving around because I'm moving around, but for all intents and purposes, it's a short. Okay, there it is. Now, if I touch the anodized portion of the aluminum, unless I scrape down all the way through it, it somewhat holds without shorting. Okay, so they probably got away with this because of the thick anodized coating of the aluminum heatsink. However, certainly not the way we want to do this. These really need to have the mica pads on them. And as you can see, one of the 3 transistors had this pad. Okay, it's in pretty good shape yet. The other 2 did not. And I can tell that these transistors have been replaced. One of them even doesn't match the others. Also, when I read them, at least with the little semiconductor analyzer, this thing's not really super trustable for transistor gain and so forth, but what I found is the gain was pretty different on them. This one only had a HFE of 11, this one was 48, and this one was 39, which these are pretty close, this 39 and the 48. The 11's a little bit low. And, you know, gain on transistors can vary quite a bit, so I'm not super concerned about it, but the good news is none of them are shorting, none of them are leaking. So, that being said, I don't know what the breakdown voltage is of this anodization, but for sure it's not something I want to play with. We're going to fix that. So I just thought that'd be interesting for you all to see. But that may be one of the reasons this thing didn't just go up in a big puff of smoke as soon as they turned it on. You're only talking about 30 or 40, about 40 volts going into this, so maybe they lucked out on that. I don't know. So, okay, I'm going to continue, and I will be back. Okay, moving some stuff out of the way for you here. I've got my transistor curve tracer connected up. You can see it down here. It's nothing special. You saw the video on it. And we're going to look at how we can match up or compare the values of these transistors. Now here's how we do it. We connect the transistor to the curve tracer. So we have the emitter and the base and the collector. And if we want to do the math, we can. But really all I'm concerned about is each step where it's located on here. And you can see it's going up 1 to about 3 divisions, just under 3 divisions. Okay? Now, again, I'm not even going to do the math to figure out the beta on this. We're just going to do a basic test. Same thing, we pull another transistor, emitter, base, and collector. And when we look, it's a little bit higher, but similar. Okay? So those would have similar gain characteristics. This one's got a little more gain than the other one. We go to our next one. Base collector, and if you look, almost no gain at all. And funny, if you look at this, I didn't even look at it, but take a look. There's the one that measured on my semiconductor analyzer as having HFE of only 11. So what that tells me is under an actual load, okay, which is what this curve tracer does, that transistor does underperform. So what would be the correct action for this? Well, first of all, if we look at this schematic, okay, let's back off here. If we look at the schematic here, and I'm going to turn my scope down here. If we look at the schematic, you have 4 that are actually your power outputs, and then 2 of those transistors are drivers to pretty much increase the gain. So you're actually making kind of like your own Darlington pair, if you will. Not exactly, but kind of. Alright? So what we're doing is we're using this first transistor to increase the gain for these 2 outputs. If we were to put that low gain one here, and we had another one on here that was more of a normal gain to the other ones, you would already start out with an imbalance. Okay, and that would cause distortion. If you put them in one of these positions, you may not notice it as much because the way these things run, the gain isn't as big of a factor. Okay, so what I'm going to do is I'm going to match all of these transistors and measure them in that way. I got 3 more on the other side, and I'm going to try to arrange them in such a way that we balance things out. Now, if this doesn't work out, or if I find one that's grossly out like that again, I may scrap the whole idea. I think I have 12 NPN transistor power transistors that will work, or 6 of them, I'm sorry, 6 transistors, 12 if I have to do both amplifiers, that I could replace all of them. But I really don't want to burn through my stock of what I have unless I have to. Now, if I need to, I will. These amps to me are worth it. There's some sentimental value because they're out of my church. And, you know, we want to see everything work again. But we'll play it by ear here and see how it goes. So I just thought you'd like to see that. So you can see where that little curve tracer that I built down here, and check my video out on it if you haven't already, pretty much correlates with this little transistor analyzer. Now, the only thing I like about the curve tracer better than this is you have a visual representation of what's happening in the transistor, so you could see noise and things like that a little better, I would say. The other thing is it puts more current through the transistor, more of a real-world test through it than this little analyzer. Obviously, this thing runs on a little button cell and doesn't really put out much current, but it does work. And you can see that if you just had one of these, and they're expensive for what they are, they're $70 to $100, but they do work, and they are pretty accurate. So anyways, I'm digressing again. Basically, we have 2 transistors that are pretty tightly matched, and then we have a third one that is pretty low on the gain. So if you were trying to use a matched transistor set in this amp, you would not be using this set that you see here. The other thing is I dug out some of my silicon heatsink pads. Some people really cringe when they see these, and in a high-powered amplifier like a a big industrial amp that's super high power, I probably wouldn't use those. They don't work as well as the grease and the mica pads. But for this application, this thing doesn't run very warm. You're getting 100 watts out of 4 pretty powerful transistors. So I really don't think that anything's running too hard, and I think these will be able to adequately carry the heat away. Doesn't have as good of thermal coupling as grease, but it is pretty good, and it will work for this application, and it's not as messy, and it's permanent. You don't ever have to worry about it. So anyhow, that's where we are, and I will come back when we have a little bit more. I'm about to resolder this one wire, this brown wire, onto here. I've already cleaned it off, twisted it around there, but I just wanted to say, if you invest in a bottle of this RA flux, you can buy it very inexpensively. RA is rather non-corrosive. You can see it's very thin stuff. It's not paste. But put a drop on this terminal. These terminals are old. They get tarnished. And what a difference it's going to make when you go to solder it. Now, it's going to throw some smoke. Wait till the iron gets up to temperature here. But when you go to flow the solder on there, you can see how nice and neat that is. I mean, I can zoom right in on it, and you can see it, come on, focus, does a very nice job. It's nice and silver, no pitting on it, no dullness looking to it, and that's going to give you a really good solid joint that's not going to fail on you. And then I just put a little piece of heat sink over this because I don't want this to touch when, you know, moving around in there or whatever. I know I'm doing a little bit of overkill here, but again, I don't want to have to come back and ever do this again. I want this thing to outlast me. So hit it with the heat sink gun, the heat shrink gun, and we are good to go. And there you have it. So now I'm going to go ahead and reassemble all this, put the transistors back in, and see how it looks. I'll be back. I've decided to make a little change here. I really didn't like that one transistor that was only a beta of 11. It was just too low. So I went through and I have some NTE 130s, which equate to a 2N3055 115 watt transistor. And what I'm going to do is I have two of them that are almost identically matched. And I am going to use these in place of the driver transistor for each of these. Now, these are very similar gain-wise, just, you know, a little bit lower, or a little bit higher gain, not much, than the output transistor. So one of these I'm going to use on this heatsink. The other one I'm going to use on the other heatsink to make sure that our driver section is very well matched. Again, like I said, if the outputs are a little bit mismatched, we're not really going to worry about that so much. But we are going to worry about the drivers being equal. And you don't want a massive difference. That one with the gain of 11, it's just going to cause the other transistor to take more of the load. So again, it probably wouldn't make a huge difference in the output, but it might. So this is what we're going to do, and I'll use these, you know, use the aftermarkets here as the drivers because they're very well matched, and that should really make this amp perform a lot better. So okay, we're going to keep plugging along. I've ohmed out the transformer long ago to verify it was good because I didn't even want to start this project till I knew that. I did that at the site, which is why you didn't see me doing it. Well, what I've done right now is I've disconnected all of the diodes. They're all getting replaced anyways. And I replaced the thermistor, and the biggest one I had was a CL90. I don't know if you could see it in there. You can see where I soldered it in. Got rid of this old, this broken one. And I'm hoping the CL90 will be big enough for the application. I'm pretty sure it will be, but if it's not, it'll get real hot and I'll order a different one. Anyways, we're going to plug this in. Now, what I have this hooked up to right now is a dim bulb tester, and I know I've showed that to you guys before, but those of you who are new to electronics or doing service, all a dim bulb tester is a power socket, you know, an electrical outlet, which, let me flip you around here. You can kind of see plugged in down here. Okay, I'm not gonna, but basically there's an outlet under here, right here, and in series with one of the prongs of the outlet is a light bulb. Okay, so the theory behind that is, if we plug this in and we have a dead, let's say we had a short, like a dead short on a winding or something, what you would see in there is that that light would light up brightly. All the current would go into the bulb rather than into the windings of the transformer. And if there is something shorted, rather than burning more components up, all that you're going to do is you're going to light the bulb up. If the bulb does not light up, that means there's very low current because the bulb actually is a high resistance, and basically that means that the circuit's going to power up under low current, and you should get a rough idea of the voltages on the windings. Now I went one step further with my dim bulb tester, and I put a big toggle switch in there, and all the toggle switch does is it shorts out the light bulb, which basically makes that whole outlet be just like an extension cord. So it's just, you're going straight to your 120 volt AC line then. So once I know everything is safe, I can flip that and put full power. And I also have a fuse socket in line with that, with a fuse, so I can change that fuse out to whatever value I want. So even with the bulb out of there, if I exceed a certain current of that fuse, I'll blow the fuse rather than blow up my device that I'm testing. So it's just a really cheap, easy way to test things, and I find it just quicker and easier than using a one of those up here, my Variac and isolation supply and all that. So it's just an easy way to test things, and if all you're trying to do is protect against shorts, it'll work. Now with all the diodes, I lifted them all out of the circuit. What that means is by doing that, none of the power out of the transformer is going to get over to the circuitry or to the capacitors or anything. So all we're going to do is power up the transformer so we can measure the windings. Okay, so I'm plugging in here right now, and we're going to check to see if our bulb lights up. So let's look at the bulb here. And I'm going to plug in right now. And you can see it didn't even flicker, didn't even flash, nothing. It is totally out. Okay. I go down here, and either I have nothing here or it's very low current. So let's look at the meter. Okay. So I'll put this in. Excuse the glare. I'm going to move this out of the way for a minute. Okay, so you can see where we're at. And if I measure this winding right here, there's 55 volts, 55.2. I measure this winding. I'm going to scroll down a little bit. This winding is 174 volts. Okay, so this is the high voltage. I'll show you on the schematic here in a minute. And I think that's really the only windings, the only two real windings we're concerned about. Now if we look here, right here is going to be your 50 volt winding, 55 or whatever. Now again, I only have that dim bulb in there, so it's going to be higher than that under full load and full power. But this is the winding here, from here to here, that's going to generate your plus and minus 38 volts for your power. This is your high voltage low current section, and that's those smaller diodes that have never been replaced. And you can see right there, that's going to be, when it's done through all these resistors and so forth, is going to be 106 volts. Okay, so right away I can tell that this is very close to what we need it to be, and I would say that this transformer is good. So I don't need to go any further with that, unless it shorts under load or something, but that's very rare that that happens. So we're good. I'm going to unplug this, and we're going to move on now to doing our other set of transistors. I'm kind of putting the cart before the horse a little bit. I really wanted to check the transistors if I needed to order anything, but I just wanted to check the actual voltages on the windings, even though I statically ohmed them out earlier. I wanted to replace that CL90 now that I have remounted the thermal cutoff switch. And by the way, there is a thermal cutoff switch on this heatsink, not on this one. And what that's there for is if the transistors go into thermal runaway, which that doesn't happen very much with silicon as much as it did with germanium diodes, but this will get really hot, and that switch is just a bimetallic strip of two dissimilar metals. When they get hot, they drift apart and break the contact, which would basically shut power off to the machine. So it's just kind of a safety. The other thing is if you're overloading the amplifier, running it at max volume or something, transistors start to overheat from overdriving them. It'll eventually shut the amp off till the transistors cool back down. So it's safety circuit. So this is a very well designed amplifier for its age. It has lots of redundant safety on it. Between the thermistor, which will actually protect your transformer especially from the surge of these capacitors charging up when you first plug it in. That's what this is for. And a thermistor is nothing but kind of a resistive device that when you first turn it on, it's a higher resistance. Okay, there's go low ones and go high ones. This one's a go low. So it has kind of a resistance to it. When you first turn the power on, current will flow through this, and since there's resistance in there, that current will actually heat this up, because of course current gets converted into heat in a resistor, when you dump current into a resistor. And that heat, this resistive material is designed to change with temperature. So as it heats in a CL90, that resistance will drop, and it'll go down almost to nothing, just a couple of ohms. And then it'll act like it's no longer in the circuit. So that's what that's for. But for that split second that it's warming up, it's actually limiting the current through the transformer. So that's protecting your windings of your transformer, and it's protecting your whole circuit when those capacitors charge, so they don't charge so quickly that it wipes out the windings of your transformer. So that's what that all is. Let's get on to these other transistors and test them and put them up on the tester, and then we will go from there. And I'm just basically going to do the same thing to this as I did with this. Same test with the curve tracer. I'm going to put my hand-picked driver transistor in there and replace it, and clean all the other ones and test them, find the two best matched ones, and hopefully they'll both be in the 30s, 40s range to match these two outputs. Put them in the output sections and put my driver in the driver section, and as soon as I do all that and reassemble, I'll come back. Just a real quick update here. I got this other heatsink out, and as you can see, the driver transistor, this is the position for the driver, has already been replaced with a different one. So obviously we had something wrong at some point in time, and it's actually an ELM130, which I'll bet you probably will cross over to a NTE or ECG 130. So somebody already had my idea the last time they worked on this and replaced it. Again, I'm going to put the mica pads in, the silicon pads I should say, clean this all up real well, put my new transistor in here and beta check these ones, make sure they're good. Okay, if I have big problems with these, I'm going to get 4 nice matched output transistors and just replace them all. So we'll see where we are. Well, as we can see, short circuit on red and blue. So we actually have a emitter to base short on this one. So our transistor is bad, and that doesn't surprise me because once again, none of these are on insulating discs, and I expected we would probably have some problems here. So we definitely have a bad driver transistor, and who knows what we're gonna find on this. I hope these are good because I really don't want to replace them if I don't have to. I ended up replacing the transistors with some new ones because they were just too unmatched. They probably would have worked, but I just want to make sure this thing works right. So we got a new CL90 thermistor installed. I got all new, as you can see down here, I replaced the diodes, put the little bypass capacitors on there for the noise, and I'm ready to fire this thing up and just check the voltage and see where it's at, and hopefully we'll get some DC on here and see what happens. So I'm just reading across the two main capacitors. I have not replaced them yet. They're not shorted, they're just reading really, really, really low, so I should be able to see something here. So let's plug it in and see what we get. And again, I'm going through the dim bulb, so we're going to check this with with some current limiting. Okay. So on our negative line, I'm getting negative 35, and I should have negative 38. And with full power, I know I'll get that. And if we look up here, I'm getting negative 35 there. So I'm getting, or plus 35, I'm sorry. So I'm getting my plus and minus 35, 38 volts, whatever you want to call it. So that's all good. Let me unplug this now. So I'm pretty confident that power supply and everything is going to be okay. Obviously, we're going to need to recap this, get rid of these bad capacitors. I'm still not totally sure how I want to handle it. Looking at this, I have these 12,000 microfarad 63 volt 105 degree caps. They're a little bit dinged up, you know, they're new old stock, but they're good caps, and they'll kind of just fit right over here. So I need to just fabricate some kind of a holder. I want it to look fairly neat. I mean, this is all going to be enclosed anyways, you're not going to see it, but I don't want to drill any holes in this very old collectible chassis, and I do want to make it so that if we ever wanted to restore it to original, we could, or at least close to original. I mean, this has been worked on a lot over the years, but it really hasn't been mechanically modified, and I really would like to keep it that way if I could. So I'm going to probably solder some terminal strips onto these existing tabs and disconnect the caps and connect it up that way. Again, it won't look you know, factory, but it will work. It'll be safe, it'll work well, and it'll be reversible if we need to do that. So that's kind of my decision on that. For right now, though, I think we're good with this section. I'm going to kind of focus now on this board, and the main reason I want to do that right now is I know I have capacitors to finish this part, so I'm not worried about it. If I do need to order components for this, however, I'd rather find that out sooner than later. So I'm going to do this board, measure all the components, make sure they're good, and get it all cleaned up and repaired. And then if everything's good from there, we'll go ahead and finish the power supply. So I will be back. Well, at this point in time, all I can say is wow. Here's where we are with this board. You can see I've been replacing this. I'm not shotgunning this thing. I'm replacing the components that actually tested bad. Of this entire board, one transistor was not shorted or open. These are both bad. I mean, I know you guys can't believe this. I have to connect one to show you. So we go here. And you turn it on. Short circuit. Sorry, the lead fell off, but short circuit. So turn this, go to this one, turn it on. Common cathode diode network. It's not reading as a resistor or as a transistor. Here's a little NPN transistor. Let's try it. Cathode diode network. It's got an open leg again. Let's try this one. Unknown faulty component. I mean, this is what this whole thing has been like. Many of these components, as you can see, were just hacked in, kind of the way they were soldered. You can see this capacitor blew out. This one's leaky. One of the diodes on here was shorted. These were old glass diodes. They're actually supposed to be silicon, and they're signal diodes, so I replaced them with the 1N4148s. Looking at the voltages and everything on there, they should work. These right here are the correct replacements, but I didn't have the ones that had the built-in heat sinks. So these are the correct transistors, but I will have to order the clip-on type heat sinks. They do make them. So I'm going to order those. It's going to be about $3 or $4 for those, but that's not bad. Surprisingly enough, every one of these resistors tested good. So obviously these are not the cheap carbon composite. These are good quality resistors. So I left them alone. I am really not a fan of ceramic capacitors, especially in the signal path. But it looks as if this amp, for the most part, is a direct coupled amplifier, meaning that you don't really have capacitors coupling the signal path. Basically, these are only used for bypass. And so I'm not going to mess with them. I'm not going to change them. This is a really neat designed amp. The more I work on it, the more I appreciate the design, and the more I appreciate Macintosh. These guys are amazing. Of course, with all the things I've had to replace and rebuild on this, it's going to be a miracle if it works. But I'm going to keep plugging along. Again, I got the other part. The only thing I need to replace is the two big capacitors that are bad down there on the main amp chassis. And we should be pretty close to testing this out. It'll be safe to turn this on and test it without heat sinks on this. I wouldn't run it long term like that. I'll get the little clip-ons for that. But as you can see, this is what I've been fighting. The other thing, I don't know if any of you guys have ever tried to convert any of this over, but these transistors do not have part numbers as per se. It says it's an RCA, but if you look really close, it just has a part number 039, and what you have to figure out is what that stands for is a 132-039, which is the Macintosh part number. Then you have to go to the Macintosh semiconductor manual. They do have one. And I just printed a page out so you can see what I'm talking about. And you can see down here 132-039. It's obsolete. The first choice would be replace it with a 132-146, which is another Macintosh part number, RCA 40410. So you look up on RCA 40410, and then you have to translate that over to like an NTE or something that you can recognize, and it comes all the way back around to a NTE 129 or a SK 3025, something like that. So it's a basic transistor, but you have to go through all this. They also have layouts of the components, so the pinouts. So then you have to go to the pinout page, because you see this is diagram number 12 right here. And then we go over to here, and it shows you the pinout of the transistor. So if we go like this, we have emitter, base, collector. So then you have to translate that over to your new transistor, make sure it's pinned out the same. So just getting one transistor converted to a modern replacement is a lot of work. It's a research project. And this is what I've been doing here for the last 2 days, just to get these couple, you know, in my spare time here, like I have any, just to get this replaced. So these are done. The beauty of this is once I'm finished, I'll know what components I used, and if this functions, then the second amp's going to be a piece of cake, because I know the formula, how to do this. The other thing is this heatsink, the built-in heatsink on this transistor, actually is a conductor. If you look under here, you see I had to put these blue wires on, and basically you're jumpering this pin over here to over here, because it actually acts as a jumper. So I had to make sure I put jumper wires in there, because I don't have the solder down heatsink. So this is a lot of work. Something that looked really fairly simple turned out to be quite a project. But slowly but surely we're winning the race here. You know what they say, slow and steady wins the race. That's what we're doing today. So as soon as I get the rest of this figured out, we're going to go ahead and get the board fitted back into the chassis. And that's it. Now these were replacement transistors, and if you look at them, let's see, I have one that you can actually read. It's a JAN, which means Joint Army Navy, so it's a military spec transistor, and it is a 2N1026. That was another difficult one. These test on my transistor tester as Darlingtons because they're messed up. The base is messed up on them from all the shorts and things that were in here, and from just the mess of the repairs that have been done. And so I finally figured out what this was, and these two transistors I used here turned out to be equivalents. They are NTEs, but they're new old stock NTEs, back when NTEs were still fairly decent. I checked them on my tester, and they're beta matched pretty close, so I don't think we're going to have any problems with that. Anyhow, there we are, and that's our update for right now. I still have to deal with this, which has been replaced once before, this little tiny diode, if you can see it. I'm not sure what it is. It's another research project. They're calling it a reference diode. Not all the other ones are calling signal diodes or rectifier diodes. This one's called a reference diode. Now I don't know if that's some slang term for a Zener or what, but I'm going to, and again, it's a replacement part, which means I can't really even go by the GE number on this, because this may have been replaced with the wrong component, whoever did it. So I'll have to go all the way back to this semiconductor chart again, look it up, and figure out what it is. I have a feeling a 1N4148 will work, just like it did for these other ones. They're fast switching diodes, and they handle the voltage that I see in the circuit here. But again, I don't know. Maybe it's some weird diode. Maybe it's a Schottky. I don't know, because, who knows? But I'm going to look it up. Anyway, that's where I'm at. And once we get some power applied to this or something more to see, we'll be back. Thanks a lot, guys. Okay. So here's where we are. I just want to give you a quick update on this component here. The 070-040 diode here, this little one, is called a stubistor. If you look at it, its location is D3 and D4, so it's this one in the schematic. It's this one right here, you can see. And its whole purpose in life is to create a voltage drop of about 1.2 volts. And essentially what's inside of here is two diodes in series. So I don't know if any of you have ever worked on some of the newer, old now, 1970s, but the Pioneer stereo amplifiers. They have those odd looking square diodes that are three diodes in series. It's a reference. Basically, it's a voltage reference is what they use it for. So really, and if you look here, that jives with this, because if you look, what they're looking for here at the base is 1.2 volts. It says it right there. Now, so basically, this should read like two silicon diodes in series if it works properly. So if I put my probe here and I look at my meter, 1.24. So as you can see, this is a good diode, first of all, so we don't have to replace it, and second of all, we've verified what it is. But if this were bad, I would just take two of these 1N4148s, which have a voltage drop of about 0.6 or so, and I would just put two of them in series right in place of this, and it will work just fine. So that's what that is. Like I said, that's not an uncommon thing. I've seen it in the Pioneer amplifiers a lot. They use them like in the SX 1050s and 750s and all that. They put those in there, and they use that to have an accurate voltage reference. So that's kind of what that is, and mystery solved. I am going to now say that this board is complete, and we can test it now. There we go. I've got some capacitors fitted in here now. Instead of the original down here 9300 40 volt capacitors, I've upgraded to a nice set of 105 degree 12,000 microfarad 63 volt. These will last forever in here. We shouldn't have any problems. I did put some hot snot in here and some zip tie pads to secure everything down, but you can do the little rubbing alcohol trick, and this will all pop right off if we ever need to remove it. But it's real secure, it won't go anywhere like this. I lifted all of the terminals from the positive lead of each capacitor so they're effectively out of the circuit, and just fastened a terminal strip. Just use the screw terminal of the capacitor as a holder for a terminal strip, and I moved the power wires to that. So everything here is reversible. We can put everything back to factory if we ever decide to do that. That's important on this because it's such an old unit. Probably could have done a prettier job, made things look neater and more professional and whatever, but I'm going for reversibility. Okay, and this will work just fine as it is, and it'll last. So I'm going to flip this up and get our rebuilt driver board fitted, and turn it back over and put some power to it, see what happens. I will be back. I've got this thing all put together now, and I have it hooked up to a 16 ohm load. So basically all I did was I took my little dual 8 ohm stereo load. Let me get you out of the stand here for a second. Right here. And I just basically tied those two 8 ohm loads in series to give me a 16 ohm load. Then I followed the little directions here for the jumpers. I made myself a couple little, temporary jumpers and tacked the wires on. Tacked on an AC cord. As you know, we've tested the voltages and they all look good. Got some heat sinks on the little TO5 transistors there. And we're ready to test this out. Now, again, phone. Okay, I'm back. So, everything's all together. I have, let me take it off the stand again here. I have my 1 meter set for the negative voltage power supply. This one's set for positive going power supply. You can see right there how we're wired in now. We have our capacitors set up. Like I said earlier here in the video, I made everything reversible. Put the little bypass caps onto the diodes. Doesn't look beautiful, but it's functional and it should be good, and there's a big cover that covers this whole thing anyways. So here we go. Let's turn this on. I'm going to feed a let's try a 400 hertz tone into this, because I want to see at about 400 hertz where we are. And let's see here. And I'm going to put about, I'm going to start out with we're going to start out with about 10 millivolts. Sorry while I get set up here. And we'll start bringing everything up. So let's plug it in. As you remember, there's no power switch on this because this is an industrial version of the MC100. I'm going to plug this directly into my isolated transformer power supply. Let's see what happens. And as we can see, I've got my minus 35, my plus 35 there, pretty close. So they're pretty well matched. And let me get my oscilloscope. I'm going to go to about 2 volts per division for starters. And I'm going to zoom you in on my scope, and I'm going to start slowly bringing this up to see what kind of input we're going to get. Well, so far, nothing. How about that? Alright. So I am getting no signal here. So let's regroup a little bit and see what's going on. And I'll be right back. Okay, note to self. It really helps when you turn the output to your signal generator on before you start cranking it up. So as you can see, we have a minimal signal going into about 10 millivolts going into the input of the amplifier. And so far we're seeing everything's looking pretty good. Let's spread this out a little so we can see the waveforms a little better. And alright, go to 5 volts per division. And right there we start seeing some noise, and you can see how it's starting to oscillate on the one side. Now let's connect the voltmeter and see what kind of voltage we're getting just before it breaks up. See how much of... So right there, one click before it starts, I'm getting about 4.5 volts. So let's turn this off. So at about 4.5 volts, let's see here. So 4.5 times 4.5. So at about 2.5 watts, it starts to break up and make some noise here. Let's just see what we get. And just so you all know, I was putting 450 millivolts in, and I was an RMS. Okay, we're talking all RMS, and we're getting 4.5 volts RMS out. Okay, so as we can see, this amplifier is working properly, whereas we're getting you're basically getting a 10-to-1 ratio out. Okay, so basically that's how the amp is working right now. So basically with a 2-volt signal going in, you're going to get 20 volts out, which is about right for this amp. Now, why are we getting this noise? Let's turn the output back on. I'm going to drop this down to about 400 millivolts. And as you can see, now I'm going to go in 100 millivolt steps. The top half is working very well. Okay, we're back here. So I was sitting there checking that, and as I turned the camera off, because my wife came down to ask me a question, the magic smoke came out of this heatsink. And as it turns out, one of these resistors burned open, namely this one. But when I measured this one, it was open as well. This one's not open, it's high resistance. This one is open. I'm wondering if maybe this one always was open. I don't know. Now, here's the crux of the situation, and that is I'm going to measure these transistors, make sure they're still good. Nothing really got overheated or anything. But now that I have bad resistors, I'm going to just replace them all with the same kind. There are 0.3s that are in there now. The only ones I have available are some 0.15s, and I have some pretty odd-shaped PC board mount 0.33s. The only problem with this is I think these are going to be kind of messy to try to hack them in there, and really they're for current limiting, and the new transistors are way overrated from the old ones, so I think they'll handle a little bit extra current spikes. So I don't think these 0.15s will be that bad. They'll still do their job. If it shorts out, it'll open the resistor. So I'm going to test these transistors now. I have the first one pulled out, and I'm just going to connect it up to the transistor analyzer. Short circuit. So our transistor shorted out. So that's going to be the first problem. If we look, it's shorted red, green, and blue. All three are shorted. So we have problems there. And I'm sure when I go down the list I'll find some more problems. I'm really going to more closely scrutinize how this was wired up to make sure that there aren't any wiring faults. The other thing I'm noticing is this little socket here is broken, as you can see. And it was like that. I noticed when I took it apart, it felt kind of loose. So we're going to kind of have to go down the line here and correct all these problems on the outputs. The good news is I think everything's going to be fine on the driver board and the preamp board. I kind of poked around on that a little bit. It looked good. So I'm just going to do a complete rebuild of this circuit right now. And then I'll be back. Okay, good news. We only had one shorted transistor. And here's the scenarios, what I think happened. I think this was loose to begin with, but I don't think that caused the problem. I think it came the rest of the way loose when I lifted it out, but I could be wrong. The bigger issue is one of these two resistors was open. This one here was open. By it being open, it was unbalancing the load because it was putting all the load on this transistor here. And if you look at the way they do this, and I don't really understand it, but even though these are ganged together, outputs, it goes through, this one goes directly to the center, of the push-pull circuit. This one goes through another current limiting resistor. So what that does is it kind of unbalances the load between these two transistors. Now, I don't really understand why they did that. I don't have a full explanation, but basically what we did was this resistor here is open. This resistor here was not. And, well, actually I take that, yeah, this resistor here was open. So all the current was going through here, which was causing our weird imbalance through this current limiting resistor. That's what was causing that thing to oscillate funny on the negative swing, which made sense. I thought I measured all these resistors, but I may not have. They looked good, so I measured one or two, and so that's what you get. I mean, when there were so many bad things with this, you just can't trust even one component in this amp. There were so many problems. So again, I'm going to redo these. I only had to replace the one transistor, which is this one here. I'm sorry, this one here, which shorted, and then blew this one out, or made it go real high. So these all have to go. One of these is already replaced. I took care of that. And this side here seems to be working just fine. I'm not having any problems with the positive swing, but I do have to replace these resistors now to make all this match. So, in a nutshell, we're doing the resistors. I did one transistor, rewire it back up, and I think this time we might have a winner then. As it turns out, it was only one bad resistor, so I just replaced it in there. I got this thing turned on. All my voltages are perfect. Watch now what we get. You see if I can get both things in the shot here together. This meter here and the scope. And as we crank this up, it just keeps going and going and going, and I got 40 volts. So, big time power. So, yeah. So let's just run it there for a minute. that would be 27 volts RMS. So let's just check that real quick. That'd be 91 watts. So this bad boy was cranking out 91 watts with absolutely no distortion, and I could have just easily kept going if I wanted to. So let's go over one. You can see right there's where it's clipping at about right there, 44.4 volts. So let's check that out, 44.4 volts. Oh, gotta be right back. Okay, had a phone call. Read 'em and weep. I did the math, and I am getting a pure 123.2 watts into 16 ohms. This amp is phenomenal. I've never seen anything perform like this before. Super duper amp. So anyhow, I have one last little thing I want to correct, and that is I'm not sure with this, or over here, if you look at the CL90, I think this CL90 gets a little bit too warm. It doesn't get like leave skin on it when you touch it, but it still gets really hot. So I may put another CL90 in parallel, but I don't like doing that for these because that doesn't work very well. I may just have to get a bigger, just a larger sized thermistor, but we'll see what happens. Anyhow, other than that, the amp is done, it's working, and we're ready to start on amplifier number 2 and to look at the preamp too as well. So good news all around. Okay, one last shot here. This is the money shot. We're going to do 20 volts per division on the scope, and here we go. Right about there is our clipping point, and I am at 44 volts just about, and everything's looking real good. So at 16 ohms I'm getting 120 watts out of this 100 watt amp. Unbelievable. I think the combination of the capacitors, but I do, yep, definitely have to get rid of that CL90. It is definitely not capable of handling that kind of power. You can see down here, let's see if we can get the thermal infrared thermometer on here. Right now it's about 97 degrees Fahrenheit. And that's with no power. But you can see pretty rapidly when I start cranking this up. It starts climbing really fast. Look at that. See that? So, and it'll just keep going till it burns up. So we definitely got to take that out of the circuit. Let's take a look at something here for a minute. We'll unplug this, and if we look at our power supply here, I'll be right back. So as you can see, this is the input of the power transformer, and here's the thermistors they have. Now this is a dual power. This one is obviously not wired like that, but it's just to pick up surge so it doesn't mess up the transformer. I just think this is going to cause more problems than it's going to solve. So I am going to take it out of the circuit and We're just going to hope for the best. I don't think, I mean, none of the other amps out there have those. This is just added protection. I think part of that was in there because the older diodes were much, much smaller than this. They couldn't handle the current surge with the capacitors. Everything is modern now. We don't have those kind of problems anymore. So I think I can do away with this and it will work just fine. So we're going to try it, make sure everything's good, and then button it up. Alright, I've hooked up the preamp and it's got a little bit of an issue. I'm running it right now at about 18 watts RMS output to 16 ohms. Or no, wait a second. Actually about 9 watts actually. Okay, sorry, I'm back. So I've been slowly turning this up, if people quit coming down here all the time. And I'm just running it right now at about 25 watts RMS into 16 ohms from the preamp. Now if you notice, I don't know if you can see that or not, but you see how there's like a little bit of jitter up and down? And if I turn the bass up, it does it even more. I think there's something, a noisy component in there, and it's putting a very low frequency oscillation into there, and that's causing the transistors to heat up more than they should. Now they're not, as you can see here, they're not by any stretch of the imagination getting super hot. I mean, the heat sink's warm, but I would expect it to be warm with 25 watts continuous into 16 ohms. That's a lot of power we're dissipating, and it's handling it no problem. But again, when I don't use the preamp, I don't get that jitteriness. The other thing I'll have you take a look at is, if you look, I'm only running 2 millivolts, and actually I can drop this down to 1 millivolt RMS into the scope. Let's see where we're at here. And I can crank this volume up and I can still get almost full power. And actually, if I adjust this a little bit, the gain of the amplifier itself, you can see I can get power, 1 millivolt, more than enough to drive this thing, 25 watts. So there's all kinds of gain in this amp. Alright, and what I'm just doing here is I'm just giving it a little bit of a soak test just to see how it holds up. And like I said, the heat sinks are warm. I mean, I can hold my hand on it, but they're warm. They're pretty warm. And again, I don't know how long I would run it like this, but more than enough to play the bells. And again, I think these things just are going to run hot like that. 16 ohms is a heck of a load, and you're driving that big matching transformer and all that. That's a lot of power that those transistors are dissipating right now. So I would expect them to get rather warm. But as it is right now, it's working fine. The sound is very clear and undistorted, with the exception of that hum that I'm getting in the preamp, which we're going to fix that. But again, this all looks really good. It's working very well. The other thing is this the impedance on this frequency generator, signal generator, is low impedance, like 50 ohms, and this preamp is really designed for a high impedance input, of a like a tape head or a magnetic phono cartridge, something like that. Very high gain. So yeah, everything's looking good, and I think this amp's ready to be put together. And then I'm going to go into this preamp, which is powered off of the main amp. You can see there, really weird design. They run like 90 volts down into this, and they run it through resistors, a whole bunch of stuff. But yeah, let's get it buttoned up. Alright, I'm going to wrap this one up. As you can see, I changed these resistors. One of them was really noisy. I also swapped out these first two capacitors. They were 80 microfarads. I put hundreds in there. I don't really think that they were all that bad, and I just realized this is a 100 volt at 200 microfarad instead of 200 microfarad at 100 microfarad at 200 volts, so that's got to get swapped. But anyhow, I found a CL30 that I had. Works perfectly in here for the inrush current. Amp is working completely perfectly, so I'm going to put the right cap in here, button it up, and this one's done. And then we're going to move on to the second amp, and I'm going to post this one up there right now, and then the next video we'll start with looking at the preamp outputs and everything. And get the preamp done, and then we'll start on the second amp, get it done, and we'll be ready to put it back into the bell tower. Okay, better. All I had was a 450 volt capacitor at 100 microfarads. This one's a 350. But it'll work. It's just way overkill. A little bit bigger, but that's okay. It's nice and secure. It's in there, and we are ready to button this thing up and start on the preamp. So I'm going to upload this video now, and the next time you see this, it'll be all assembled and we'll be working on the preamp. Thanks for hanging with me on this one. It was a real challenge, but this is an awesome amp now. Just cannot believe how it performs. Alright, see you next time.